There's a place where water exists without flowing, where darkness has remained unbroken longer than light has existed anywhere else. The surface above shows nothing, white stretching into white, horizon blending with sky until the boundary disappears completely. But beneath that emptiness lies weight, not the weight of stone or metal, the weight of time itself pressed into layers, compressed until it becomes something else entirely. The cold here is not like cold anywhere else on Earth. It doesn't bite or sting. It simply removes. Heat vanishes. Sound vanishes. Even the air seems to thin into nothing. What remains is pressure, silence, and beneath it all, something that should not exist. The ice above this hidden world measures more than 2 miles thick in places. Stacked snow from millions of winters, each flake adding its small weight to an impossible total. The mass of it pushes downward with a force that bends the earth itself. Beneath that crushing presence lies a landscape no one has walked. Valleys deep enough to swallow mountains. Ranges that stretch for hundreds of miles. Lakes larger than entire countries. All of it sealed away in darkness. The distance between the surface and what lies below is not just vertical. It is temporal. The ice carries within it the breath of ancient atmospheres. Air from eras when the planet looked entirely different. And below that frozen archive, where the ice finally meets rock, water moves. Slow, patient, inevitable. We measure depth in meters. But numbers stop meaning anything after the first kilometer. The mind cannot hold that much absence of light, that much pressure, that much time. Every assumption about how water should behave fails here. It flows uphill when the ice demands it. It remains liquid at temperatures that should freeze anything. It connects systems separated by distances too vast to comprehend. The tools we build to explore this world break. Not from violence, from patience. The ice simply waits for metal to weaken, for batteries to drain, for signals to fade. Then it closes over the intrusion as if nothing had disturbed it. Our most advanced instruments last days in an environment that has endured for epochs. The imbalance is absolute. What lies beneath the South Pole's ice is not a single mystery. It is layers of mysteries, each one hidden inside the next. Geography that exists only as echoes. Rivers that flow without sound. Life that persists without light. And throughout all of it, a question that refuses simple answers. Why can we not reach it? The answer is not about technology alone. It is about balance, about the friction between what we want to know and what knowing might destroy. Beneath the ice, something waits, not for discovery, but for understanding careful enough to preserve what it finds. Welcome to Info Jungle. If you enjoy calm, thoughtful documentaries about the natural world, consider subscribing. These videos are created to help you relax while learning at a gentle pace. The South Pole exists in a different relationship with distance than anywhere else on Earth. Stand at its exact point, and every direction is north. The concept of west and east dissolves completely. Even the sun refuses to follow the rules that govern the rest of the planet. For 6 months it circles without setting. For the next 6 months it vanishes entirely. Time itself behaves strangely here. The mind struggles to orient itself when day and night cease to function as boundaries. This is the first hint that the rules governing familiar places do not apply. The ice sheet that covers Antarctica is not simply frozen water stacked on land. It is an entity of its own. An ice mass so vast it contains 90% of Earth's frozen water. If it were to melt, global sea levels would rise by nearly 200 feet. Every coastal city would vanish beneath waves. The weight of that ice, measured in quadrillions of tons, presses down with such force that the continent beneath has sunk. The bedrock that once stood at sea level now sits in basins hundreds of meters below it. The ice created its own geography by simply existing. What makes this ice sheet different from glaciers elsewhere is its age. The oldest ice near the bottom has been frozen for more than 1 million years. Within it, trapped in microscopic bubbles, is air from epochs when the Earth's atmosphere contained different gases. Scientists who extract cores from deep within the ice can analyze that ancient air. They can measure carbon dioxide levels from before humans walked upright. They can detect volcanic ash from eruptions that reshaped global climates. Every layer tells a story about the planet's past. But those stories exist only because the ice preserved them perfectly. The cold here does not degrade or decay. It suspends. Beneath the surface layer, where wind carves the snow into patterns called sastrugi, the ice transforms. Snow that falls compresses under its own accumulation. Air spaces between flakes collapse. Crystals fuse together. What begins as light powder becomes dense glacial ice. The deeper you descend, the denser it becomes. Eventually, the ice turns so compact that light cannot penetrate it. The world below exists in total darkness. The South Pole Station sits on a plateau nearly 2 miles above sea level. The altitude makes breathing difficult for newcomers. The cold makes every task exhausting. Machinery brought here must be modified to function in temperatures that can drop below -70 degrees Celsius. Plastic shatters like glass. Metal contracts and warps. Electronics fail without extensive heating systems. Even fuel thickens into sludge unless treated with special additives. Every supply must be flown in during the brief summer months when planes can land. Once winter begins, the station becomes completely isolated. No flights arrive or depart for 8 months. The people who choose to winter at the South Pole do so knowing they are committing to absolute solitude. If something goes wrong, there is no evacuation. The cold and darkness make rescue impossible. This isolation is not theoretical. It is total. What draws scientists to endure these conditions is what lies beneath the ice they walk on. Radar mapping has revealed that the bedrock under the Antarctic ice sheet is not flat. It is a complex landscape of mountain ranges, deep valleys, and vast basins. Some of these mountains rise thousands of meters high. Others plunge into trenches deeper than the Grand Canyon. All of it remains hidden. The ice above conceals one of the most dramatic terrains on Earth. Among the most striking discoveries are the subglacial lakes. These are bodies of liquid water trapped between the ice sheet and the bedrock below. They exist despite temperatures that should freeze them solid. The pressure from the ice above, combined with heat from the Earth's interior, keeps the water liquid. Scientists have identified over 400 of these lakes across Antarctica. Some are tiny, no larger than a pond. Others rival the Great Lakes in size. The largest, Lake Vostok, lies beneath nearly 4 kilometers of ice. It contains more water than Lake Ontario, and it has been sealed away from the atmosphere for at least 15 million years. The existence of these lakes raises immediate questions. If water exists there, could life exist as well? On the surface, life depends on sunlight for energy. Plants photosynthesize. Animals eat plants or each other. Energy flows from the sun downward through ecosystems. But beneath the ice, there is no sunlight, no photosynthesis, no plants. If life exists there, it must survive through entirely different chemistry. This possibility has profound implications beyond Antarctica. Jupiter's moon Europa is covered in ice. Beneath that frozen crust, scientists believe there is a global ocean. Saturn's moon Enceladus has similar characteristics. If microbes can survive in Antarctica's subglacial lakes, then perhaps life could exist on those distant moons as well. Studying what lives beneath the South Pole's ice becomes a way of understanding what life might look like elsewhere in the solar system. But reaching those lakes presents extraordinary challenges. Drilling through kilometers of ice requires enormous equipment. The drills must remain sterile to avoid contaminating the water below with surface bacteria. They must generate enough heat to melt through ice without introducing chemicals that could alter the lake's chemistry. They must maintain pressure balance so the lake water doesn't rush upward when breached. Each of these requirements pushes engineering to its limits. The first attempts to drill into Lake Vostok took decades. Russian teams working at Vostok Station spent years lowering their drill bit deeper. They used a mixture of kerosene and freon to prevent the borehole from refreezing. But these chemicals posed a contamination risk. When the drill finally broke through to the lake, the pressure forced water upward into the borehole. It mixed with the drilling fluid and refroze almost instantly. The sample recovered was compromised. Scientists could not be certain whether what they found came from the lake or from their own equipment. Other teams learned from this. At Lake Whillans, beneath the Ross Ice Shelf, researchers used a different approach. They melted their way down with hot water instead of drilling. The water was filtered and sterilized continuously. Every piece of equipment was cleaned with ultraviolet light. The operation required a mobile laboratory transported across the ice by tractor. When they finally reached the lake, they collected samples with extreme care. What they found astonished them. The water contained living microbes, tiny organisms feeding not on sunlight, but on minerals dissolved from the bedrock. They were metabolizing iron and sulfur compounds, converting chemical energy into biological activity. It was proof that life could exist in complete darkness, in isolation, under conditions that seemed impossible for any ecosystem. This discovery changed how scientists think about life's requirements. Light is not essential. Warmth is not essential. What matters is chemistry, energy in any form that organisms can harness. The microbes in Lake Whillans had adapted to their environment so completely that they no longer resembled surface life. They moved slowly. They reproduced slowly. Everything about their biology reflected the constraints of their world. But they endured. The implications reach beyond biology. If life can persist in such extreme isolation, then perhaps the subglacial lakes are not unique. Perhaps similar environments exist in other extreme locations on Earth. Deep underground, beneath ocean floors, inside solid rock. Each new discovery expands the boundaries of where we expect to find life. The Antarctic ice sheet becomes not just a frozen wilderness, but a window into life's adaptability. Yet with each discovery comes a deeper ethical question. Should we explore these places at all? Every time a drill penetrates the ice, it creates a connection between the surface and the hidden world below. That connection, however carefully managed, introduces risk. Surface microbes could enter the lake. Chemicals from equipment could alter the water's composition. Even the act of drilling changes pressure and temperature in ways that might disrupt delicate ecosystems. Scientists must weigh the value of knowledge against the cost of obtaining it. This balance defines modern Antarctic research. The continent is governed by the Antarctic Treaty, signed by dozens of nations. It designates Antarctica as a place for peaceful scientific research only. No military activity. No resource extraction. No territorial claims. Every research project must demonstrate that its methods minimize environmental impact. The treaty represents a rare moment of global cooperation. Nations that disagree on nearly everything else have agreed that Antarctica should remain protected. But protection does not mean leaving it completely untouched. It means approaching it with care. The ice sheet is not static. It flows constantly toward the coast at rates varying from centimeters to meters per year. As it moves, it grinds against the bedrock below. This friction generates heat. That heat melts small amounts of ice at the base, creating a thin layer of water. This water acts as a lubricant, allowing the glacier to slide more easily. The process is self-regulating. More friction creates more heat. More heat creates more water. More water allows faster movement. The system maintains its own balance. But that balance is delicate. Small changes in temperature can shift the entire system. If surface temperatures rise, more meltwater can seep down through cracks in the ice. This additional water can accelerate glacier flow. Faster flow means more ice reaches the ocean. More ice in the ocean means rising sea levels. The feedback loops connect Antarctica's interior to coastlines thousands of miles away. Understanding these connections requires understanding what happens at the base of the ice. Where ice meets rock. Where pressure meets heat. Where frozen meets liquid. This boundary zone, invisible from the surface, controls much of Antarctica's behavior. Scientists use radar to study it. They send radio waves down through the ice and measure how long they take to return. Smooth surfaces reflect signals cleanly. Rough surfaces scatter them. Liquid water creates distinct reflection patterns different from solid ice or rock. By analyzing these patterns, researchers can map the hidden landscape. They can identify lakes, rivers, and channels beneath the ice. They can track how water moves through the subglacial system. They can even detect changes over time as lakes fill and drain. This remote sensing allows exploration without physical intrusion. It provides knowledge without contact. In many ways, it represents the ideal form of exploration for such a fragile environment. Yet radar has limits. It cannot reveal everything. Some areas are too deep or too complex for signals to penetrate clearly. The data requires interpretation. Different teams analyzing the same radar results can reach different conclusions about what lies below. The hidden world beneath the ice remains partially unknowable. We see its outline but not its details. We understand its general shape but not its precise nature. This incompleteness is both frustrating and appropriate. It reminds us that some knowledge must be earned slowly. That understanding does not come from a single breakthrough, but from decades of patient observation. The ice teaches patience simply by existing. As winter settles over the South Pole, the darkness becomes complete. The sun disappears below the horizon and does not return for months. Temperatures plummet further. Wind speeds increase. The few people who remain at the research station live in a world reduced to essentials: warmth, light, communication, work. Outside, the continent continues its slow transformation. Snow falls in compresses. Ice flows toward distant coasts. Lakes fill and drain beneath the surface. Rivers of melt water trace invisible paths through darkness. None of it requires human observation to continue. The system operates on time scales that dwarf human lifetimes. What we see in our brief visits is a snapshot of processes that have been unfolding for millions of years, and will continue for millions more. The South Pole's ice holds its secrets not out of malice, but out of nature. The pressure that seals the subglacial world also preserves it. The cold that makes exploration so difficult also keeps ancient ecosystems intact. The darkness that prevents visibility also protects delicate chemistry from disruption. Every barrier to exploration is also a form of protection. Every difficulty we encounter is the environment maintaining its own integrity. Perhaps that is the most important lesson the ice offers: that some places resist easy access precisely because they are worth preserving. That the boundary between us and what lies beneath is not an obstacle to overcome, but a balance to respect. There is a map of Antarctica that shows the continent as it would appear without ice. The coastline changes completely. What we think of as a single landmass becomes an archipelago. West Antarctica fragments into islands. East Antarctica remains intact, but reveals valleys deeper than any canyon visible on Earth's surface. The map looks alien, like something from another planet. Yet this landscape exists right now beneath the ice. It is real terrain that no one has ever seen directly. The maps are built from echoes, radio waves sent downward through kilometers of frozen water. The signals bounce back carrying information about density and distance. Computers translate those echoes into images. But the translation is never perfect. Some areas return clear signals, sharp boundaries between ice and rock. Others return noise, scattered reflections that could mean anything. A layer of sediment, a pocket of water, an anomaly in the ice itself. The map makers must decide which interpretation makes the most sense. They compare data from different years and different instruments. They look for patterns that repeat. They eliminate obvious errors. What remains is their best guess at what lies below. The map is revised constantly. Each new survey changes details. Valleys shift position by kilometers. Lakes appear where none were expected. Mountain ranges extend farther than previous estimates suggested. The revision never ends because the ice never stops moving. The landscape beneath it flows and deforms under pressure. What was accurate last year may no longer be true. The map of Antarctica's hidden interior is always provisional, always incomplete. This uncertainty affects everything built upon it. Scientists trying to model ice sheet behavior need to know the shape of the bedrock. They need to understand where valleys channel water, where ridges block flow, where basins trap sediment. But if the map keeps changing, the models must change with it. Predictions about future ice loss carry error bars measured in meters of sea level rise. The difference between catastrophic and manageable depends partly on details we cannot pin down. The hidden landscape refuses to be fully known. In East Antarctica, there is a region called the Aurora Subglacial Basin. It stretches for hundreds of kilometers beneath some of the thickest ice on the planet. Radar mapping suggests it contains multiple deep trenches connected by channels. If the ice above it were to melt, the basin would become an inland sea. Water would fill it to depths exceeding 300 meters in places. But confirming this requires assumptions about how radar signals behave in ice of varying temperatures and densities. Different assumptions produce different maps. Some show the basin as a single unified depression. Others show it fragmented into separate troughs. The truth remains suspended between interpretations. Scientists describe this state as working with ghost data, information that seems solid until you examine it closely. Then it becomes suggestion rather than certainty. The Aurora Basin might be one vast connected system, or it might be several smaller systems that appear connected only because of how radar waves scatter. Without drilling down to confirm, both possibilities remain open. The ice preserves its ambiguity. Beneath the Transantarctic Mountains, which divide East and West Antarctica, lie valleys that may have been carved by ancient rivers. Before the ice sheet formed 30 million years ago, Antarctica had a temperate climate. Forests grew across much of the continent. Rivers flowed to the sea. When the ice arrived, it buried everything. The valleys that once carried water now sit entombed. Some of them extend for hundreds of kilometers. Radar can trace their general paths, but not their precise depths. The signals become confused where ice transitions to rock, or where sediment layers create false echoes. Geologists studying these buried valleys try to reconstruct what the continent looked like before freezing. They use the incomplete radar maps to identify drainage patterns. They compare those patterns to modern river systems elsewhere. They make inferences about where ancient coastlines must have been. But every inference depends on the radar data being interpreted correctly. And the radar data itself is never unambiguous. The valleys might be shallower than they appear. They might connect differently. They might not be river valleys at all, but depressions carved by the ice itself. The past remains as hidden as the present. What complicates the mapping further is that ice does not behave uniformly. Near the surface, it is cold and brittle. Deeper down, under pressure, it becomes plastic. It flows like an extremely slow liquid. At the very base, where pressure and geothermal heat combine, it can become temperate, close to its melting point. Each layer refracts radar signals differently. The waves bend and scatter as they pass through. By the time they return to the surface, they carry information from multiple depths mixed together. Separating those signals requires sophisticated processing. Algorithms that attempt to correct for the bending and scattering. But the algorithms depend on assumptions about temperature profiles and ice crystal structure. Assumptions that cannot be verified without drilling. The mapping becomes circular. You need to know what is below to interpret the signals correctly. But you need to interpret the signals correctly to know what is below. Scientists break this circle by making educated guesses. They use ice cores to measure temperature gradients. They use models to predict how pressure affects ice density. They compare their maps to the few places where direct measurements exist. Slowly through iteration, the maps improve. But improvement is not the same as certainty. The hidden continent remains stubbornly resistant to complete revelation. One of the strangest features revealed by radar is a region near the South Pole where the bedrock sits more than 2,000 meters below sea level. The ice above it is over 3,000 meters thick. If you could stand on that bedrock, you would be under more than 5,000 meters of material. The pressure at that depth exceeds 400 atmospheres. Water there would not freeze at 0 degrees Celsius, but at temperatures below -10 degrees. The weight of the ice depresses the freezing point. This means that liquid water can exist at temperatures that would freeze it anywhere else. The boundary between solid and liquid becomes fluid itself. Ice and water coexist in a state that defies simple categorization. Glaciologists call this pressure melting. It is one reason the base of the ice sheet is not frozen solid to the bedrock. The pressure creates melt even when the temperature seems too cold. That melt water lubricates the ice's movement. It forms thin films between ice and rock. In some places, it pools into lakes. In others, it flows through channels carved into the bedrock or ice. The entire system operates in near-total darkness. No light has penetrated there for millions of years. Yet the water remains liquid and mobile. Scientists trying to understand this system face a fundamental problem. They cannot observe it directly. Every measurement must be indirect. They can detect changes in surface elevation as lakes fill and drain below. They can measure slight variations in gravity as water redistributes. They can record seismic tremors as ice shifts or cracks under pressure. But they cannot see the water itself, cannot measure its temperature directly, cannot sample it without disturbing the very system they want to understand. The hidden hydrology of Antarctica operates beyond the reach of direct observation. It must be inferred from consequences rather than observed as cause. This creates a strange relationship between scientists and their subject. They are detectives examining a crime scene where they cannot enter the room. They must reconstruct events from evidence collected outside. Footprints in the snow that suggest movement within. The evidence is real. The conclusions drawn from it are reasonable. But the gap between evidence and certainty remains. Some of the subglacial lakes appear to be connected by channels. Water flows from one to another over years or decades. Satellite measurements show the surface of the ice rising above one lake while sinking above another. The implication is clear. Water has moved between them, but the channel itself cannot be seen. Its size, shape, and exact path remain unknown. Models suggest it might be a tunnel melted into the base of the ice, or a crack in the bedrock through which water seeps, or a thin film spread across a wide area. Each possibility produces the same visible effect. A lake drains while another fills. The system balances itself through pathways that resist direct detection. This invisible hydrology controls how fast the ice sheet moves. Where water accumulates, the ice slides more easily. Where water drains away, the ice sticks to the bedrock. Small changes in water distribution can accelerate or slow vast sections of the glacier. And those changes happen continuously. Lakes fill and drain on irregular cycles. Some shift every few years. Others remain stable for decades before suddenly releasing their water. The triggers for these releases are not fully understood. Perhaps pressure builds until it exceeds some threshold. Perhaps temperature changes alter the balance. Perhaps the ice's own movement creates conditions that open or close pathways. The system is self-organizing in ways that defy simple prediction. Attempting to model it requires simulating processes that cannot be observed. Equations describe flows through geometry that remain uncertain. Parameters must be estimated rather than measured. The resulting predictions carry inherent uncertainty. Scientists can say what might happen under various assumptions, but they cannot say with certainty what will happen. The ice keeps its own counsel. Another source of uncertainty is the geothermal heat flux. The Earth's interior radiates heat toward the surface. In most places, this heat dissipates into the atmosphere or ocean. But beneath the Antarctic ice sheet, it contributes to melting at the base. The amount of heat varies, depending on the underlying geology. Areas with volcanic activity produce more heat. Regions with thick continental crust produce less. The variation matters because it determines where basal melting occurs. More heat means more melt water. More melt water means faster ice movement. But measuring geothermal heat flux beneath kilometers of ice is nearly impossible. Scientists use indirect proxies. They estimate heat flow based on the age and composition of rocks sampled at the continent's edges. They use seismic data to infer mantle temperatures below. They compare Antarctica's geology to similar regions elsewhere. But all of these methods produce rough estimates with large error margins. The actual heat flux at any given location might be significantly higher or lower than predicted. This uncertainty propagates through every model of ice sheet dynamics. A region thought to be cold and stable might actually be warm and active. A lake presumed isolated might be connected to a vast hydrological network. The hidden world beneath the ice contains too many variables that cannot be constrained. In West Antarctica, there is a glacier called Pine Island. It has been retreating rapidly for decades. Warm ocean water is melting it from below. The ice shelf that once buttressed it has thinned. Without that support, the glacier flows faster toward the sea. Models attempting to predict how much ice Pine Island will lose depend critically on what lies beneath it. Is the bedrock sloped downward inland? If so, warm water could penetrate farther, accelerating collapse. Are there ridges that might slow the retreat? Channels that might drain melt water away or concentrate it? Radar maps provide some answers, but not all. The bedrock topography near the grounding line where ice meets ocean is complex and difficult to resolve. Different interpretations of the data produce different predictions. Some models show Pine Island stabilizing within decades. Others show it collapsing completely within a century. The difference amounts to meters of global sea level rise. And the uncertainty stems partly from incomplete knowledge of a landscape buried beneath the ice. This is what dislocation feels like. The sense that everything you thought was solid begins to shift. Maps that seemed reliable reveal their limitations. Processes that appeared straightforward turn out to be complex. Questions that seemed answerable remain suspended. The hidden world beneath Antarctica does not yield to straightforward interrogation. It resists being known in the ways we are accustomed to knowing things. You cannot walk across it, cannot photograph it, cannot point to it and say with certainty, there. It exists in a state between confirmed and theoretical, real but unverifiable through direct experience. The scientists who work with this uncertainty develop a different relationship with knowledge. They become comfortable with ambiguity. They learn to state conclusions with appropriate hedging. They distinguish between what the data strongly suggests and what it merely permits. Their papers are filled with phrases like "may indicate" and "consistent with," and requires further investigation. This is not weakness or evasion. It is intellectual honesty in the face of profound unknowability. The ice teaches a kind of epistemic humility. It reminds researchers that certainty is often a luxury unavailable in complex natural systems. That understanding comes in degrees rather than absolutes. That the map is never the territory, especially when the territory itself refuses to be mapped completely. Yet despite all this uncertainty, patterns do emerge. The subglacial lakes cluster in certain regions. The deepest valleys trend in particular directions. The ice flows toward the coast following predictable pathways. There is structure beneath the chaos, order within the ambiguity. The challenge is discerning which patterns are real and which are artifacts of measurement, which features are stable and which are transient, which processes are dominant and which are secondary. These distinctions require judgment as much as data, experience as much as analysis. The longer scientists work with Antarctic data, the better they become at reading its ambiguities. They develop intuition about what seems plausible. They recognize when results are too neat to be trustworthy. They learn which uncertainties matter most and which can be safely ignored. This accumulated wisdom cannot be taught directly. It emerges from years of confronting the ice's resistance to easy answers, from building models that fail in instructive ways, from comparing predictions to observations and discovering where the mismatches lie. The process is slow and often frustrating, but it is also the only path forward. Because the alternative, claiming to know more than the data supports, leads to mistakes with global consequences. So the work continues. Radar surveys fly over the ice during brief summer seasons. Satellites monitor surface changes from orbit. Ice cores are extracted and analyzed for clues about basal conditions. Computer models grow more sophisticated, incorporating better physics and more detailed geometry. Each advance reduces some uncertainty while revealing new layers of complexity. The hidden landscape comes into slightly sharper focus, but it never becomes completely clear. There is a kind of patience required here that goes against human instinct. We want answers. We want to know what lies beneath and to know it completely. But the ice does not operate on human timescales. The processes unfolding below happen over centuries and millennia. The water flowing through subglacial channels moves centimeters per year. The lakes filling and draining do so over decades. The ice sheet itself is adjusting to climate changes that occurred thousands of years ago. Everything operates in slow motion by our standards. Yet the consequences of these slow processes ripple outward rapidly. Ice that took millennia to accumulate can be lost in decades. Sea levels that were stable for thousands of years can rise meters in a century. The disconnect between the pace of change beneath the ice and the pace of consequence above it creates a temporal dissonance. We measure fast effects from slow causes and try to predict future fast effects from slow causes we cannot fully observe. The entire endeavor requires projecting forward from incomplete understanding. It requires making decisions with global impact based on maps that remain provisional. This is the heart of dislocation. Not just that we cannot see what lies beneath, but that what lies beneath determines outcomes we desperately need to predict. And the tools we have for seeing are limited. The patience required exceeds our natural scope. The timescales involved dwarf our planning horizons. We are forced to act on incomplete information, because waiting for complete information means waiting too long. The ice will not wait for us to finish mapping it before it responds to the warming we have already caused. So scientists do their best with what they have. They quantify their uncertainty and include it in their models. They provide ranges of outcomes rather than single predictions. They communicate clearly about what is known with confidence and what remains speculative. And they continue, returning to Antarctica season after season, collecting more data, refining their instruments, improving their understanding incrementally, knowing that the complete picture may never come into focus, but also knowing that every piece of information matters. Every new measurement constrains the possibilities slightly. Every corrected map improves the models slightly. Progress happens in small steps across a landscape that sprawls beyond human scale. Beneath the ice, the hidden world continues its existence independent of our efforts to comprehend it. Water flows where pressure drives it. Ice deforms under its own weight. Lakes fill and drain according to physics that does not require human understanding to function. The system operates with or without our attention. Our observations do not change its behavior, only our understanding of it. And that understanding, hard-won and incomplete, is what allows us to anticipate rather than simply react, to prepare rather than be surprised, to respect the scale of what we face rather than underestimate it. The dislocation is permanent. We will never stand on the bedrock beneath the South Pole, never see the lakes with our own eyes, never touch the water that flows in eternal darkness. But we can listen to echoes. We can measure shifts and changes. We can build understanding from fragments. And in that fragmentary understanding lies our only path forward. Not certainty, not complete knowledge, but sufficient insight to navigate a changing world. The ice teaches by withholding, by remaining partially hidden, by forcing us to accept that some questions have only provisional answers, that some maps will never be finished, that some depths cannot be fully plumbed. And perhaps that is exactly the lesson we need. In a world where we have grown accustomed to satellite images showing every square meter of Earth's surface, where we expect immediate answers to every question, the existence of a vast hidden landscape teaches restraint. It reminds us that knowledge is earned through patience. That understanding is built slowly. That some mysteries persist not because we lack technology, but because the nature of the mystery itself resists easy resolution. Beneath the South Pole's ice lies a world that will remain partially unknowable. Not forever, perhaps, but for now. And the now stretches beyond any single human lifetime, perhaps beyond several generations. The ice keeps its secrets not through malice, but through simple physics, through the crushing pressure that makes direct observation impossible, through the vast scale that defeats comprehensive mapping, through the slow pace that defies quick answers. And in keeping those secrets, it teaches something more valuable than any single fact could provide. The understanding that limits exist, that not everything yields to investigation. That respect sometimes means accepting what cannot be known. At least not yet. Perhaps not ever. The dislocation is complete when you realize that this is not a problem to be solved. It is a condition to be accepted. The hidden world will remain hidden even as we learn more about it. We will see through the ice more clearly. But we will not see everything. And that partial vision, that incomplete understanding, is what defines our relationship with what lies beneath. Not conquest, not mastery, but witness, imperfect and ongoing. In the darkness beneath the ice, temperature holds steady near freezing. Not fluctuating, not seasonal, constant across thousands of years. The water molecules move slowly through that cold, their motion limited by pressure and proximity. Each molecule surrounded by others in densities that approach solid without quite reaching it. The boundary between liquid and frozen exists as gradient rather than threshold. What flows does so reluctantly. Viscosity increases with depth and pressure. Water that should pour becomes syrup. Syrup becomes something thicker still. Movement happens, but at rates measured in millimeters per day. Sometimes less. The current has no surface to disturb. No ripples. No waves. Just the slow displacement of mass through space, following gradients too slight to perceive. Where pressure eases fractionally, water moves toward that relief. Where ice melts above, fresh water trickles down into the column. Where minerals dissolve from rock below, density shifts create gentle circulation. These forces would be invisible even if light existed to reveal them. They operate below the threshold of anything humans call current. Yet they are sufficient. Enough to transport dissolved gases across kilometers. Enough to distribute nutrients between distant parts of the lake. Enough to prevent complete stagnation. The water does not need to rush. It needs only to continue. At the bottom of these lakes lies sediment. Fine particles ground from bedrock by the glacier's passage. They settled here over millennia, each grain descending through the water column at speeds too slow to calculate meaningfully. Days to fall a single meter perhaps. Years to reach the bottom from the ice ceiling above. The sediment forms layers, each one representing a span of time during which conditions remained stable enough for particles to accumulate. Darker bands might indicate periods of increased melting. More particles carried into the lake as water flowed faster temporarily. Lighter bands suggest quieter times. Less input. The lake settling into deeper stillness. These layers hold information, but not the kind that can be read easily. No tree rings marking years. No ice layers with trapped air bubbles. Just gradations in composition too subtle to date, without extensive analysis. The sediment is not inert. Microbes live within it. Organisms so small that millions would fit on a pinhead. They cluster around particles of specific minerals. Iron-rich grains attract certain species. Sulfur compounds attract others. Each microbe occupies a chemical niche, extracting energy from reactions between water and rock. Their metabolism proceeds at rates matching the environment. Slow, measured not in hours between cell divisions, but in months, sometimes years. A bacterial colony in surface soil might double every 20 minutes under ideal conditions. Here, the same process takes a season, perhaps longer. Time stretches. Biological processes that seem fundamental become optional at this pace. DNA repair happens eventually. Proteins fold slowly into functional shapes. Waste products diffuse away gradually. Nothing requires speed. Speed would be wasteful. Energy is too scarce to spend on haste. The microbes that thrive here are those that learn to wait, to persist through spans of inactivity that would kill most organisms. Their cellular machinery is built for endurance rather than efficiency. Enzymes function at near-freezing temperatures where most would denature. Membranes remain flexible despite cold that would solidify others. Genetic repair systems work continuously against damage that accumulates slowly but never stops. They are adapted completely, not to light and warmth and abundance, but to dark and cold and scarcity. This is normal here, the only normal that matters. In some lakes, the water contains dissolved gases from ancient atmospheres. Nitrogen and oxygen and carbon dioxide in ratios that no longer exist at the surface. These gases were sealed in when the ice formed millions of years ago. They diffused slowly down through the ice column, accumulating in the liquid below. The concentrations build over time. Pressure keeps them dissolved at levels that would bubble out violently at sea level. But here under 400 atmospheres, they remain locked in solution. A microbe feeding on dissolved nitrogen encounters abundance. More nitrogen than exists in most surface environments. It processes the gas slowly, converting it through metabolic pathways into forms its cells can use. The excess is released back into the water, creating a cycle that has no beginning and no end. Just continuation. The chemistry is not exotic. The same reactions happen in surface soil and ocean sediments. But here they proceed in darkness, without oxygen from photosynthesis, without organic matter from dead plants and animals. The entire system is stripped to essentials. Rock provides minerals. Water provides medium. Pressure provides stability. Geothermal heat provides energy through temperature gradients. Nothing else is required. The lakes exist in a state of minimal sufficiency. Enough of everything necessary. Excess of nothing. Between the lakes, channels carry water. These are not caves in the conventional sense, not hollowed spaces you could walk through. In most places, they are gaps at the ice-rock interface, millimeters to centimeters high, extending for kilometers in length. The water within them moves under pressure gradients created by the ice weight above. Where the ice is thicker, pressure increases. Water is forced toward areas where ice is thinner. The flow follows the path of least resistance, sometimes along cracks in the bedrock, sometimes in grooves carved by previous flows, sometimes through porous sediment layers that allow seepage. The channels are not permanent. They shift as the ice moves. A pathway that carries water one decade might close the next, as ice flow compresses it. New routes open elsewhere as pressure redistributes. The network is constantly rearranging itself, maintaining overall connection, but never settling into fixed geography. Mapping these channels from the surface is nearly impossible. They are too small for radar to resolve clearly, too variable to predict from models. Their existence is inferred from effects. Lakes that drain must be releasing water somewhere. Lakes that fill must be receiving water from somewhere. The channels are the necessary connection, present by logical requirement, even when invisible to measurement. Along some channels, The ice above melts continuously. The friction of flow generates heat. Small but cumulative. Over decades, this heat can widen a channel from millimeters to meters, creating tunnels within the ice rather than gaps at its base. These tunnels conduct water more efficiently. Larger volumes flow faster. The increased flow generates more heat. More heat widens the tunnel further. The process is self-reinforcing until some limit is reached. Perhaps the tunnel grows large enough that ice flow compresses it closed. Perhaps the water source feeding it diminishes. Perhaps pressure patterns shift and the flow redirects elsewhere. The tunnels are temporary features. They collapse and reform on timescales of years to decades, each one existing for a moment in glacial time, then vanishing as if it never was. Where water flows fastest, minerals precipitate from solution. Calcium carbonate, silica, iron oxides. They form thin crusts on the ice walls, building up slowly. Microscopic layers accreting over centuries. These crusts trap bubbles and particles, creating records of flow conditions. If they could be extracted and studied, they would reveal details about water chemistry over time. But they remain entombed, part of the hidden archive. The ice itself behaves differently at the base than at the surface. Near the bedrock, it is warmer, softer, more plastic. Crystals slide past each other under stress rather than fracturing. The ice flows like putty, deforming around obstacles, filling voids, conforming to whatever shape the pressure demands. In some areas, sediment mixes with this basal ice, creating a layer that is part frozen water and part rock debris. Neither quite ice nor quite sediment. A hybrid material with properties of both. It grinds against the bedrock below, abrading and polishing, while the cleaner ice above slides over it. This layer acts as both lubricant and brake. Where sediment concentration is low, lubrication dominates. The ice slides easily. Where sediment is dense, friction increases. The ice sticks. The balance determines how fast each section of the glacier moves. Small variations in sediment distribution create large differences in flow rate. A glacier that seems uniform from above is actually a patchwork of speeds below. Some sections racing forward at meters per year. Others barely creeping. All of it hidden beneath continuous white surface. The microbes living in this basal environment face different challenges than those in the lakes. The substrate is not stable. Ice moves. Sediment shifts. A microbe attached to a rock grain might be carried kilometers from where it first colonized, or crushed between ice and bedrock, or suddenly exposed to different chemistry as water flows change. Adaptation here means flexibility, the ability to enter dormancy quickly, to survive being frozen and thawed repeatedly, to colonize new surfaces rapidly when opportunity appears. These are generalists, not specialists fine-tuned to narrow conditions. They persist through versatility, through the capacity to endure disruption without dying. In the deepest parts of the thickest ice, pressure approaches 500 atmospheres. Water at that pressure behaves in ways that seem contradictory. It becomes denser than normal. Its freezing point drops to minus 15 degrees Celsius. Molecules pack more tightly. Hydrogen bonds angle differently. The resulting structure is still recognizable as water, still liquid, but altered in subtle ways, dissolving different minerals more effectively, conducting heat differently, supporting different chemical reactions. The microbes here evolved in this altered water. They have never experienced normal pressure water. Their proteins fold correctly only under compression. Their membranes seal properly only when pushed together by surrounding pressure. If you could somehow extract them and bring them to the surface, they would not survive. The release of pressure would be catastrophic. Cells would rupture. Proteins would denature. The organism would disintegrate. Not from heat or light or toxins, but simply from the absence of the crushing force they require to exist. They are pressure obligate, bound to the depths, incapable of functioning anywhere else. This is adaptation beyond what surface life achieves. This is biology completely divorced from the conditions that define habitability everywhere else. No light, no oxygen from atmosphere, minimal organic carbon, extreme pressure, near freezing temperature, total isolation, and yet life, not barely clinging, but established, cycling nutrients, reproducing, evolving slowly in response to the environment's demands. The ecosystem is complete within itself. It does not need the surface, does not depend on anything beyond rock, water, and time. Some of the lakes contain hydrogen sulfide, a gas that smells like rotten eggs and is toxic to most organisms. But here, certain microbes use it as an energy source. They oxidize the sulfide, stripping electrons from it to power their metabolism. The process is ancient, one of the earliest forms of chemosynthesis on Earth. Before oxygen, before photosynthesis, bacteria feeding on volcanic gases in the primordial ocean. The same chemistry persists here, unchanged for billions of years, operating in an environment that resembles early Earth more than modern Earth. The lakes are time capsules, not just of atmosphere and geology, but of biology. They preserve metabolic pathways that have been supplanted elsewhere. Microbes here might be living fossils, lineages that survived by retreating to the only places where their ancient chemistry still works, where competition from more efficient organisms never penetrated. Studying them is studying the deep branches of the tree of life, the roots from which everything else descended. But the study must be done without killing them, without contaminating their environment with modern microbes, without altering the chemistry that sustains them. The difficulty is absolute. To see them is to change them. To sample them is to introduce variables they have never encountered. So they remain mostly unobserved, known from fragments of DNA extracted with immense care, from chemical signatures in water samples, from inference and educated speculation. The direct view is withheld, not by choice, by necessity. Above the lakes, within the ice, there are layers where the crystal structure changes, boundaries between ice from different eras, each layer formed under different atmospheric conditions, different temperatures, different pressures. The crystals within those layers align in specific patterns. Radar waves passing through are refracted and scattered by these alignments, creating internal echoes that appear as ghost horizons in the data. These horizons sometimes confuse lake detection. A bright radar return might indicate water, or it might indicate a crystal boundary. Distinguishing between them requires analyzing the signal's characteristics, its strength, its sharpness, how it changes with different radar frequencies. The analysis is technical and prone to error. Some features mapped as lakes turned out to be crystal boundaries. Some dismissed as noise proved to be actual water. The ice conceals through complexity, layer upon layer of structure, each one contributing its own signature to any measurement. Parsing signal from artifact requires experience and caution. In places where ice shelves float on the ocean, seawater penetrates beneath. It flows upward into gaps between ice and bedrock, mixing with fresh melt water from above, creating gradients of salinity. The denser salt water sinks. The lighter fresh water rises. Slow circulation develops, not driven by temperature, but by density differences too subtle to create strong currents. The resulting stratification is delicate. Layers of different salinity stack vertically, each one maintaining separation through density alone. Microbes adapted to salt water occupy the lower layers. Those adapted to fresh water occupy the upper. Between them exists a transition zone where both types struggle. Neither fully comfortable, both present but less abundant. The stratification can be disrupted by changes in ice shelf thickness. If the shelf thins, ocean water penetrates farther. The salt layer rises. Freshwater ecosystems retreat upward. If the shelf thickens or flow patterns change, fresh water dominates. The salt layer contracts. Marine organisms find their habitat shrinking. These shifts happen slowly, but they happen. The ecosystem beneath ice shelves is not stable. It adjusts continuously to changes in ice configuration, to ocean temperature fluctuations, to melt rates that vary with season and climate. The organisms living there experience a slowly changing world. Not catastrophic, but never fully predictable. Adaptation means tolerating gradual drift in conditions, maintaining viability across a range of salinities and temperatures, being flexible enough to persist when the environment shifts beneath you. In the coldest parts of the deepest lakes, water approaches maximum density, 4 degrees Celsius in normal conditions. But under high pressure, maximum density occurs at different temperatures. The precise relationship between pressure, temperature, and density creates circulation patterns that seem counterintuitive. Warmer water can sink if pressure effects dominate. Colder water can rise if density gradients favor it. The lakes mix internally through processes that have no surface analog. Trying to visualize the flow is difficult. The currents move in 3 dimensions, responding to forces that are not directly visible. Pressure here, temperature there, salinity gradients elsewhere, all interacting to produce circulation that is both complex and slow. Water might take decades to complete a single circulation loop, rising from the bottom, spreading laterally near the ice ceiling, cooling and sinking again at the edges. The loop is closed. Nothing enters or leaves except through the narrow channels connecting lakes. The system is self-contained, its internal dynamics driven by the small energy inputs available. Geothermal heat from below, pressure variations from ice movement above, chemical gradients from mineral dissolution. These minor forces sustain circulation that would otherwise cease. The lakes would stratify completely, become layered and motionless. But the small continuous inputs prevent total stillness, keep the system barely active, just enough to prevent stagnation. Nowhere in these lakes does light exist, not even the faintest trace. The darkness is complete. No gradations, no shadows, just uniform black in all directions. The microbes here do not have eyes, do not sense light in any way. Their world is defined by chemistry and pressure, by the presence or absence of specific molecules, by mechanical contact with surfaces. They navigate, if that is the right word, through chemical gradients, moving toward higher concentrations of nutrients, away from waste products. The movement is not directed in the way an animal moves. It is random motion biased by chemistry. A cell drifts, tumbles slowly through the water. If it encounters favorable conditions, it slows, remains in that vicinity. If conditions are unfavorable, it continues drifting, eventually finding somewhere more suitable, or dying. There is no vision, no strategy, just chemical response, automatic and sufficient. The simplicity is profound. In the absence of light, elaborate sensing becomes unnecessary. The entire organism simplifies to essential functions: metabolism, reproduction, survival. Nothing more is needed. Nothing more would be useful. The environment strips away complexity, leaves only what works. Some lakes are isolated completely, cut off from the subglacial network by shifts in ice flow or bedrock geometry. They sit alone, receiving no input except the slow melt from ice above and heat from rock below. Whatever microbes exist in these isolated lakes have been there for the entire duration of the lake's existence, potentially millions of years, with no exchange of genetic material with other populations, no introduction of new species, no competition from outside. They evolve in complete isolation, adapting to the specific chemistry of their particular lake, becoming increasingly specialized. These isolated ecosystems might represent the purest examples of adaptation to subglacial conditions, without disturbance, without influx of organisms from elsewhere. Just the slow refinement of what works in this exact location. If they could be studied, they would show evolution at its most focused. But studying them requires drilling. And drilling breaks the isolation, introduces contaminants, destroys the very purity that makes them interesting. The paradox is complete. The most valuable scientific targets are the ones that must remain untouched. Knowledge and preservation cannot coexist. Choosing preservation means accepting permanent ignorance. Choosing knowledge means accepting irreversible change. There is no resolution, only the choice. And increasingly, the choice is preservation. The understanding that some questions matter less than what they would cost to answer. In the sediments at the bottom of some lakes, organic molecules have been detected, not from modern organisms, but from ancient ones, trapped when the ice first formed and buried. These molecules are remnants of Antarctica's temperate past, when forests grew and rivers flowed, when the continent supported complex ecosystems. The molecules degraded slowly over millions of years, but traces remain, locked in sediment, protected by the cold and pressure. They are chemical fossils, fragments of DNA, lipids from cell membranes, proteins broken down into amino acid chains, Analyzing them reveals what lived here before the ice. But the analysis requires extracting sediment samples, disturbing layers that have remained undisturbed for geologic spans. Again, the tension between knowing and preserving. Some scientists argue that extracting core samples is justified. The knowledge gained about past climates and ecosystems is invaluable. Others argue that leaving the sediments intact preserves options for future study. When better techniques exist, when extraction can be done with less contamination, both positions are reasonable. Both reflect different values about what matters most. The debate continues. But in practice, very few sediment cores have been extracted. The difficulty and expense limit attempts. The ethical concerns slow approvals. The sediments mostly remain where they are, holding their information, waiting for a future that may or may not come. The entire subglacial system operates on a knife edge of stability, not fragile in the sense of easily broken, but balanced, dependent on specific conditions that are maintained by the ice sheet above. If the ice thins, pressure decreases. Melting slows. Lakes might freeze. Channels close. The system could collapse into dormancy. If the ice thickens, pressure increases. Melting accelerates. Lakes overflow. The system might flush itself clean, lose the delicate ecosystems that took millions of years to establish. Either direction represents loss. The current state exists only because conditions have remained relatively stable for long spans. As climate changes, that stability is questioned. The ice is thinning in many regions, accelerating toward the sea. The subglacial world will respond, is already responding, but how it will change is uncertain. What will survive and what will vanish? The microbes are resilient. They have endured previous glacial cycles, but never at the pace of change we are introducing. The system might adapt, or it might not. There is no precedent. No way to know except to wait and see. The waiting is its own form of witnessing, observing without interfering, measuring without disrupting, understanding that we are part of what is changing the system, even as we try to study it. The ice holds everything together, maintains the pressure, maintains the darkness, maintains the isolation that allows unique ecosystems to persist. As the ice changes, everything changes. The hidden world we are only beginning to glimpse might vanish before we finish seeing it. Not from our interference, but from our influence on the climate that sustains the ice. The irony is sharp. We want to explore beneath the ice without damaging it, but we are damaging the ice itself. The protection we extend to the subglacial lakes means little if the lakes drain away. If the ice thins until pressure no longer keeps water liquid. If the entire system transforms into something else, something we did not choose and cannot predict. This is where immersion leads, to the understanding that the environment is not separate from us. That observation is not neutral. That presence has consequence even when we try to minimize it. The microbes beneath the ice do not know we exist. They continue their slow metabolism regardless. But we know they exist. And that knowledge brings responsibility. To preserve what we can. To study carefully what we must. To accept that some mysteries will remain mysteries. Not because we lack tools, but because the cost of answering is too high. The darkness beneath the ice is complete. The pressure is immense. The cold is absolute. And life persists, adapted fully, asking nothing of the surface, needing nothing but what already exists. Time, water, rock, pressure. Enough. There comes a point where questions stop forming, not from lack of curiosity, but from something closer to recognition. The ice has no answers to give that we could understand in the ways we are used to understanding. It exists. That is sufficient. Beneath the South Pole, the water continues its circulation. The microbes continue their metabolism. The sediments continue their slow accumulation. All of it happening whether observed or not, whether understood or not. The system does not require comprehension to function. It predates our awareness of it by millions of years. It will likely continue long after our instruments fall silent. There is a kind of peace in accepting this, in recognizing that the hidden world is not waiting for us, not hiding from us, simply existing in parallel, operating according to principles that need no witness. The darkness there is not absence. It is a different kind of presence, one that does not depend on light to be real. The pressure is not oppression. It is structure, the force that holds everything in place, that allows water to remain liquid where it should freeze, that compresses time and biology into forms we are still learning to recognize. The cold is not hostile. It is preservation, maintaining conditions that have persisted longer than most landscapes on Earth's surface, keeping intact what would otherwise have degraded. Every measurement we take confirms what deeper intuition already suggests, that this place is older than our categories, more patient than our instruments, more complete in its simplicity than our models can capture. The lakes beneath the ice are not waiting to be discovered. They were never lost, only unseen. The distinction matters. Discovery implies revealing something that was hidden. But these lakes were never hidden in the sense of being concealed deliberately. They are simply beyond the threshold of casual observation, existing in a space where direct human presence is impossible. Not forbidden. Impossible. The physics does not allow it. We cannot stand on their shores because there are no shores. Cannot swim in their waters because the pressure would compress us beyond survival. Cannot shine light into their depths because no light source we could bring would penetrate the ice above. Our only access is indirect, through echoes and inferences, through the faint signatures they leave in data streams, through the patience required to interpret those signatures correctly. And perhaps that is exactly as it should be. Some places exist best when approached with restraint, when studied from distance, when understood through the negative space they create rather than through direct contact. The maps we have built of the subglacial landscape will never be complete, but they do not need to be. They are sufficient to show us that something exists there, that it is vast, that it operates according to logic we can glimpse but not fully enter. The rest can remain in the realm of implication. In winter, when the South Pole enters its long darkness, the work continues. Instruments record data. Satellites pass overhead, measuring subtle shifts in gravity and elevation. Seismometers detect the faint tremors of ice, adjusting to its own weight. No humans are present at many of the most remote stations. The equipment operates autonomously, powered by generators and solar panels and batteries that will last until spring returns. The data streams back through satellite links, accumulating in servers thousands of miles away, where it waits for analysis, for interpretation, for someone to notice patterns that might mean something. Most of the data shows nothing unusual, just the steady continuation of processes already understood. Ice flowing, lakes maintaining their elevation, temperature holding constant. But occasionally, something changes. A lake drains faster than expected. An ice stream accelerates. A seismic signal appears that does not match known patterns. These anomalies become the focus of attention. Scientists compare them to previous events, build models to explain them, plan new observations to test hypotheses. The cycle continues. Question leading to measurement, leading to new question. But the pace is slower now, more deliberate. There is less urgency to reach everything immediately, more acceptance that understanding develops gradually, that some questions will take decades to answer. That patience is not weakness but method. The ice teaches this by example. It does not rush. It accumulates understanding one layer at a time, each measurement adding a thin stripe to the record, each observation contributing a small piece to a larger pattern that may not become clear for years. The people who dedicate careers to studying Antarctica often speak of it in terms that sound almost spiritual, not because they are religious, but because the experience of working there changes how they think about time and scale. When you spend months surrounded by ice that formed before your species existed, when you study water that has been sealed away for longer than human history, when you listen to seismic data recording movements too slow to perceive directly, your sense of what matters begins to shift. The urgency that drives so much of modern life fades, replaced by something quieter, more sustained. You begin to measure things differently, not in weeks or months, but in seasons and decades, in the time it takes for ice to flow from the interior to the coast, in the time it takes for a lake to fill and drain through its cycle. Your own lifespan becomes a brief window, a moment during which you can observe a tiny fraction of a much larger process. That perspective is humbling, but also clarifying. It removes the pressure to accomplish everything immediately, replaces it with the understanding that your contribution is one piece among many, that the work will continue after you. That progress happens through accumulation rather than breakthrough. The hidden world beneath the ice will outlast any individual researcher, outlast any single expedition, outlast most institutions. It exists on geological time. Our engagement with it occurs on human time. The two scales barely overlap. What we can learn in a lifetime is vanishingly small compared to what remains unknown. But that does not make the effort meaningless. Each measurement matters. Each data point constrains possibilities. Each corrected map brings the picture slightly more into focus. The work is incremental, as it must be. Some of the researchers who have spent the most time studying subglacial lakes have never actually seen one, never collected a water sample, never touched sediment from the bottom. Their entire understanding comes from indirect evidence, radar reflections, seismic velocities, chemical analysis of melt water that seeped out at the ice margin hundreds of kilometers away. They know these lakes as thoroughly as you can know something without direct contact. They can describe the water chemistry with precision, estimate the depth within meters, predict how the lakes connect to each other. But they have never been there, will never be there, cannot be there, and yet their knowledge is real, built carefully from fragments, assembled through decades of patient observation, verified through consistency with multiple independent measurements. It is knowledge of a different kind than comes from direct experience, but it is knowledge nonetheless, perhaps more rigorous for requiring such careful inference. In the end, what we know about the world beneath the South Pole's ice is this: it exists. It is vast. It is active in ways both slow and continuous. It supports life adapted to conditions unlike anywhere else. It connects to the global system through mechanisms we are still mapping. It responds to changes in ways we are still learning to predict. And it will continue regardless of whether we ever fully understand it. That final point is perhaps the most important. The system does not need our comprehension, does not wait for our approval, does not pause while we catch up. It proceeds according to physics, according to chemistry, according to the patient logic of ice and water and pressure. Our role is not to control it, not to master it, but to witness it, to document what we can, to learn what it teaches about resilience and adaptation, to carry that knowledge forward into decisions about how we engage with the rest of the planet. The ice beneath the South Pole is not unique in being hidden. There are other environments equally inaccessible. Deep ocean trenches where pressure exceeds anything in Antarctica, caves sealed miles underground, lakes beneath desert sands, aquifers trapped in bedrock. Each one represents a world operating beyond direct observation. Each one contains ecosystems adapted to conditions we barely understand. Antarctica's contribution is not uniqueness, but clarity. The ice sheet is vast enough and studied thoroughly enough that we can see principles that apply elsewhere. We can understand how isolation shapes evolution, how pressure changes chemistry, how life persists in the absence of everything we thought essential. Those lessons extend beyond Earth. The moons of Jupiter and Saturn likely have similar environments. Subsurface oceans beneath ice crusts kilometers thick, water under pressure, darkness complete, potential for life that does not depend on sunlight. If we find life there, it will likely resemble what exists beneath Antarctica more than what exists at Earth's surface. The microbes in Lake Vostok might be our best template for understanding biology elsewhere in the solar system. Not because they are alien, but because they are adapted to conditions similar to what we expect on those distant moons. Studying them prepares us, not just scientifically, but conceptually. It expands our definition of where life can exist, what forms it can take, how little it requires to persist. That expansion is valuable regardless of what we find beyond Earth. It changes how we think about our own planet, about the resilience of biology, about the necessity of preserving extreme environments even when they seem marginal. Because marginality is a human judgment. To the microbes living beneath the ice, their environment is not marginal. It is central, complete, sufficient. They do not long for the surface, do not need sunlight or warmth or oxygen. They exist perfectly within the constraints of their world. That perfection, that complete adaptation, is worth preserving. Not for instrumental reasons. Not because they might provide useful genetic material or teach us about extremophile biology, but because they represent a form of existence that has as much right to continue as any other. They were here before us, will likely be here after us. Their continuity is part of the planet's deep history. Interrupting it, even for knowledge, carries weight that must be considered carefully. As the sun begins its long return to the South Pole at the end of winter, the ice surface transforms. The first light is not bright, just a faint glow on the horizon that grows slowly over weeks. But it changes everything. The temperature remains far below freezing. The wind continues. The ice keeps flowing. But light returns. And with it, the sense that time is moving forward again. That the long pause of winter is ending. That work can resume. Crews return to field stations. Aircraft begin flying supplies. Drilling operations prepare for another season. The cycle continues. Human activity increases. But beneath the surface, nothing has changed. The lakes do not know about seasons. The microbes do not respond to light that never reaches them. The subglacial rivers continue their slow flow without interruption. The two worlds, surface and hidden, operate independently, overlapping in space, but separate in almost every other way. Our presence on the ice is temporary, a brief occupation during seasons when conditions allow. The world beneath is permanent, continuous, indifferent to the coming and going of observers. That indifference is not cold. It is simply factual. The system operates on its own terms. Our interest in it does not change its nature. Our measurements do not alter its processes. We are visitors attempting to understand a place that does not require understanding to persist. The best we can do is document carefully, interpret honestly, preserve where possible, and accept that complete knowledge will always remain beyond reach. Not because of technological limits, though those exist, but because the act of knowing completely would require intrusion that destroys what we seek to know. The paradox is final. Total access means total contamination. Perfect preservation means permanent ignorance. We navigate the space between, taking what measurements we can without crossing lines we have drawn, learning what the ice allows us to learn, leaving the rest sealed. Perhaps that is enough. Perhaps it must be. This is only one of many hidden environments shaped by isolation. Beneath Antarctica's ice, others exist that remain sealed away. In the next film, the journey continues toward the lakes hidden beneath Antarctica's ice. A world separated from the surface for far longer than the ocean below the shelves. The wind over the plateau moves snow in patterns that repeat and dissolve. Ripples form, collapse, form again. The surface is constantly remaking itself, erasing what was there moments before. Beneath that restless surface, the ice holds steady, layer upon layer compressing into time made solid. And below the ice, the water waits, not waiting for anything in particular, just continuing, flowing where pressure directs it, pooling where basins allow, supporting life that asks nothing beyond what already exists. Somewhere in that darkness, a microbe divides. The process takes months, but it completes. Two cells where there was one. both viable, both capable of continuing. The population does not grow quickly, but it persists. That persistence is its own form of success. Not abundance, not dominance, just continuation. The lake holds them. The ice seals them in. The pressure keeps everything in place. And time moves forward. Slowly, inevitably, without reference to anything beyond itself. Above, the stars wheel through their patterns. The same stars that shone when the ice first formed. That will shine when it melts. Their light does not reach the lakes. But the lakes do not need it. They carry their own continuity, independent of celestial motion, independent of surface change. The hidden world beneath the South Pole's ice remains hidden, not from secrecy, but from depth, from pressure that makes approach impossible, from darkness that needs no illumination, from cold that preserves by preventing. It will remain there, silent to us, alive within itself, a presence we can sense but never fully touch. And perhaps that is the most honest relationship. To know something exists, to respect its boundaries, to learn what can be learned without violation, and to let the rest continue in the only way it knows. Unseen, enduring, complete.